Now we are going to look into integration by parts, which is essentially trying to turn around the product rule for derivatives. In this particular video we are going to focus on the case of indefinite integrals. Of course we know that via the fundamental theorem of calculus we can get a counterpart for definite integrals. So what can we obtain from the product rule for derivatives in terms of integrals? Recall that the product rule states that to differentiate a product of two factors, we differentiate the first factor multiplied by the second unchanged, and then add the product of the derivative of the second factor with the first factor unchanged. So let's say I want to isolate one of the mixed product on the right hand side. So I get f of x times g prime of x equal the derivative of the product minus f prime g. If I integrate both sides, I get the integral of f times g prime is equal to the integral of the derivative of the product f times g minus the integral of f prime times g. Now this term can be simplified because here we are looking at an antiderivative of the derivative of f times g. So of course f times g is one antiderivative of its derivative. So we can replace that term by f times g and we obtain what we will call integration by part formula, which is that the integral of f times g prime is equal to f times g minus the integral of f prime g. Now we are often going to rewrite that formally slightly differently in a form that is a little bit easier to remember. In this formula we're going to call f of x u, and du is f prime dx, and v will be g of x, and dv g prime dx. And with this formalism the integral on the left hand side becomes u dv. Then we have f times g, which is a product uv, and the integral of f prime g becomes integral of v du. And this is what we will call the integration by parts formula. So let's see on some examples how this applies. Here is our formula, and here is an integral we want to calculate. Here there is certainly no hope in terms of using substitution, for instance. So we can, say, try integration by parts. To do that we have to pick which one of the two functions x and sin x are going to be v and u. Well, more explicitly u and dv. So one of these two terms is going to be u, the other one dv. U is going to be differentiated, dv is going to be integrated. So we need to pick in such a way that we get something simpler. So if I differentiate x, I get 1. So I simplify. When I integrate x, I get x squared over 2. I get it more complicated. On the other hand, for sin x, whether I differentiate or integrate, I get essentially the same thing, a cosine. So I'm going to pick for u x, because this is the term I'm going to differentiate, and I want to simplify the expression, and for dv, sin x dx. I need to calculate du and v. So if u is x, du is dx. If dv is sin x dx and v is an antiderivative of sin x, negative cosine x. And then, this is what I obtain applying the formula, because uv is a product of x times negative cosine x, so it's negative x cosine x. And the integral of v du is the integral of negative cosine x dx. So, I obtain negative x cosine x plus the integral of cosine x, which is sin x up to a constant. Let's look at a second example. A pretty similar one. We want to integrate x e to the negative x. Again, I have to pick what is going to be u, what is going to be dv. Again, the rule of thumb is the same. I'm trying to simplify. And so for x, to simplify, I should differentiate. Whereas for e to the negative x, I get the same complexity if I integrate or differentiate. So I'm going to integrate e to the negative x and differentiate x. So u is x, dv is e to the negative x dx. Then I have to calculate du and v. Du is dx, and v is an antiderivative of e to the negative x, which could be negative e to the negative x. Then we apply the formula. uv is a product of x by negative e to the negative x, so I get negative x e to the negative x, and v du is negative e to the negative x dx, so I get minus the integral of negative e to the negative x, in other words, plus integral of e to the negative x, and integral of e to the negative x is negative e to the negative x, so I obtain negative x e to the negative x minus e to the negative x up to a constant. Now let's look at another example. Let's say we want to integrate cosine x ln of sine x dx. Again, we need to pick what is going to be u, what is going to be dv. So cosine x, whether I differentiate or integrate, I would get the same complexity as sine. ln of sine x, well, I don't have much of a choice because I know how to differentiate ln of sine x, but we don't really know what to do to obtain an antiderivative of that. So if we're going to try to use integration by parts, then the only choice would be to take u equal ln of sine x because we know how to differentiate it. Now one remark, before we jump into integration by parts, you might say, wait a second, we can use substitution here. I can take u is sine x, and then cosine x dx is du, and I get integral of ln of u du. Well, yes, but then what are we to do with this integral of ln of u du? So because we don't know what to do with that one, I'm going to use integration by part directly on this without doing this substitution. So as I said, u has to be ln of sine x because I don't know how to integrate it. And therefore dv is going to be cosine x dx. As usual, I'm going to calculate du and v. Du is a derivative of ln of sine x. I have to use the chain rule. So I get 1 over sine x multiplied by the derivative of sine x. So in other words, I get cosine x over sine x dx. If dv is cosine x dx, v is an antiderivative, which is sine x. Then I plug things in. uv is sine x multiplied by ln of sine x. And integral of v du is the integral of sine x multiplied by cosine x over sine x dx. You see that I have sine x over sine x, that cancels out. So I end up with simply sine x ln of sine x minus the integral of cosine x. And the integral of cosine x is just sine x. So we obtain sine x ln of sine x minus sine x up to a constant. Now in the previous example, we ended up picking the natural log for the function to differentiate because we didn't know how to integrate it. Right? I pointed out that we could have used the substitution that would have led to this integral, integral of ln of u du. Can we calculate this integral? Well, we can use the same logic that we applied in the previous example. In other words, that sometimes if there is a function for which we know the derivative, then we can try to use integration by parts and differentiate that particular function. Even though integration by parts is usually something to integrate a product, certain kinds of products, and this particular integral doesn't really appear to be a product, you can always consider it as a product of a function by 1. So we know how to differentiate ln of x, so I'm going to take u is ln of x, and then dv is what remains, in other words, dx. Calculating du is just dx over x, and an antiderivative of dx is just x. Then uv is x ln of x, and v du is x times dx over x. The x simplifies out, and we end up with x ln of x minus the integral of dx, which just gives x. So we get x ln of x minus x up to a constant. Now this way of obtaining an antiderivative for certain functions for which we know the derivative is a standard trick. So In particular, the antiderivative of ln of x, you don't necessarily need to remember the result, the formula, that the antiderivative of ln of x is x ln of x minus x up to a constant. But you need to remember how to obtain it quickly, and this is just by parts. And once you decide to do it by parts, you have no choice. You differentiate ln of x because precisely you're looking for the antiderivative, so you cannot use the antiderivative. Now there are other functions where we can use the same trick.